Hi everyone, hope you're doing great. I'm just coming back to you with a video on molecular shapes, which builds off of what we learned about covalent bonding. So what we have to remember with molecular shapes is this idea that molecules are actually three-dimensional. So sometimes when we draw Lewis dot diagrams, we're drawing a 2D representation of something that is actually 3D. So you'll see here and here, oh, there we go, here and here, that I actually have something that looks a little bit more 3D than our usual Lewis dot diagram, right? So now that we know how to draw Lewis dot diagrams of a molecule, we can use them to determine the 3D shape of a molecule. I've got some examples down at the bottom of the slide here. While 2D Lewis dot diagrams are useful to look at bonding, it is important to remember that molecules are actually three-dimensional, and that is something that we often lose sight of. Here you'll see that I have two different types of 3D models. The first two, this one and this one, are what we call a ball and stick model because they've used sticks as bonds, and then they use spheres for atoms. And then this one right here is called the space filling model, where they actually don't draw in a line for the bond. They show the molecules closer together because that is actually like more representative of what molecules look like in nature. So this is probably a more accurate model for a molecule, but this is probably more widely used because it allows us to see that bond in there. So again, this is the ball and stick model here, and this is the space filling model here. Just trying to get to the next slide there. Okay, so to determine the shape, we're going to use what we call the valence shell electron pair repulsion theory, or the VSEPR theory. This sounds super complicated, but actually you know all parts of this theory, because think about what these words mean. Valence means outer, shell, outer shell. That means when we're talking about an atom, we're talking about the outer shell here. Electron, we're talking about electrons in the outer shell. Pair, well, we know that in Lewis dot diagrams, we always draw electrons as pairs. And repulsion, of course, means pushing away from. So this is a theory about electron pairs on the outer shell pushing away from each other. And that is essentially what we draw when we draw a Lewis dot diagram. Here are our electron pairs on the outer molecule, on the outer energy level, the outer shell. And when we say they repel each other, it means that this electron pair is going to push away as far as possible from this electron pair. This electron pair is going to push as far away possible from this, and so forth. So the VSEPR theory is based on this idea that molecules will arrange themselves to ensure that their electrons are as far away as possible. Okay. Now, using this theory, we're going to be able to determine the geometry, the shape, and the bond angle of a molecule. The reason I inserted this picture down here is I just wanted to remind you it is important to remember this vocabulary: lone pair, bonded pair. So that's going to be really important. Okay. Okay. So I said that we're going to be able to identify the geometry, the shape, and the bond angle. And so I just want to talk a little bit about vocabulary. The first piece of vocabulary we're going to need to know is steric number. That's most likely a vocabulary word that you haven't heard of before. That is the number of bonding sites around the central atom. Okay, notice that we're focused on the central atom. So it's the number of bonding sites around the central atom. Okay, to get that, we're just going to look at the total pairs of electrons around the central atom. But multiple bonds, so a double or triple bond, are only going to count once, because if we're talking about bonding sites, even if I have a double bond here, this double bond is only one site of bonding. So we count that as a bonding site. A multiple bond will only count once. And I'll show you how to do this counting in a minute. Okay, the geometry is going to be the general shape classification based on the steric number. The shape is going to be the actual shape of the molecule based on the number of bonding pairs and lone pairs. And the bond angle is a bond angle in degrees that's created between electrons in a molecule. So I will show you all of these things in our example, but this is going to be an important slide for you to come back to just to make sure you understand the difference between these four words. Seem to have trouble moving from slide to slide. Oh, for bond angle, I had a picture here to show you that the bond angle would be the angle between these electron pairs right there. Okay, so to determine the shape of a molecule, we use this VSEPR theory chart. You guys all have this as a reference page. It must be a colored, copied reference page in the things that I handed out at the beginning of the year. So hopefully you have this, otherwise you can always use this one as an example. But you can see here that we have the steric number, okay? And that gives us the 2, 3, 4, 5, or 6. So that's how many bonding sites we have on the central atom. Okay, the basic geometry or the geometry is always going to be whatever's written in this first column right here. So our options for geometry are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Those are our options for our geometry. Then our options for shape is really anything on this. So something could be linear in geometry as well as linear in shape. Something can be trigonal planar in geometry and trigonal planar in shape. Alternatively, it could be trigonal planar in geometry but bent in shape. It could be tetrahedral, 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 trigonal pyramidal, tetrahedral bent. So the first column is the name of a geometry as well as a shape. And then everything beyond that are just shapes. So anything here is going to be linear. Anything here is going to be trigonal planar in geometry. Anything here is tetrahedral in geometry. Anything here is trigonal bipyramidal in geometry. Anything here is octahedral in geometry. And then the individual shape are each of these individual boxes. And so it is possible for the geometry and shape to be the same, or it could be different. The key feature is that no, this table is not provided as a reference sheet on the AP exam, so we need to be familiar with it. They have in the past just randomly asked, what shape is this? And the answer is T-shape, and there is no reference chart. Now we'll have to see what happens this particular year when we're taking it at home, and technically it's kind of an open note exam. When we get more information Friday, we'll see where that goes. Okay, so to use that chart, I use a method that I call TBL. T stands for total pairs of electrons around the central atom, counting the multiple bonds as one. Technically, this is the steric number. The reason I don't call it SBL is because when I teach it in my regular class, I don't actually introduce this word steric number. And so I just always call it total pairs of electrons around the central atom. The B is going to be the bonded pairs, and the L is going to be the lone pairs. Now, please note, we will only look at the central atom. That's going to be really important to see. Okay. Once we've identified that, we're going to use the VSEPR chart. So let me show you some examples. All of this will start to make a lot more sense. Here's water. Oops. Here's water. First, I'm just going to draw the Lewis dot diagram of water. I've counted, I've checked. I know this is the correct Lewis dot diagram for water right here. Okay. I'm going to do TBL, total bonding lone, around the central atom. So I'm only looking at oxygen, which is my central atom. Around my central oxygen, you'll notice that I have 4 total pairs of electrons. 1, 2, 3, 4. I have 4 total pairs of electrons. Of those 4 pairs, 2 of them are bonding pairs. This one and this one, 1 and 3, are bonding pairs because I've drawn them as lines. So I have 2 bonding pairs. And number 2 and number 4 are lone pairs because I have 2 lone pairs on my central atom. That gives me a TBL of 422. So my geometry is going to always be based on my total, which is 4. When I look forward here, I see that when there is a steric number of 4, the geometry is tetrahedral. So my geometry is tetrahedral. My shape, okay, is going to be, let's see, I had a steric number of 4, I had 2 bonding pairs and 2 lone pairs. So that means that this is going to be a shape that is bent, okay? And my bond angle, because this is tetrahedral, I'm in the 109 range. Typically in the AP exam, they actually say 109.5 for tetrahedral. So I'm going to use that number, 109.5. Okay, so tetrahedral has a bond angle of 109.5. But for every lone pair that you have, it actually makes it a little bit smaller. So that's why you can see that they've written 109, and then when there's one lone pair, they said less than 109, and when they had 2 lone pairs, they said even more less than 109. So I would normally just say less than 109.5 degrees. Not Celsius, this is not a temperature. 109.5 degrees for my bond angle. Okay, again, I got the bond angle from this chart. Everything that is tetrahedral has a bond angle of 109.5. And the more lone pairs there are, it's just a little bit less than that. That's because more lone pairs means more repulsion, which is going to tighten everything up a little bit. Okay, let's take another example here. Here's CCl4. Putting all my lone pairs here. Cool. Okay. TBL this. Please remember only the central atom. Actually, all those dots on the chlorine don't matter. I'm only looking at my central atom, which is carbon. On my central atom of carbon, I have 1, 2, 3, 4 bonding pairs. I have 4 total pairs. All 4 of them are bonding. I have no lone pairs on the central atom. Yes, there are a ton of lone pairs on this molecule, but I have no lone pairs on this central atom. Okay, no lone pairs on the central atom. 440, total bonding lone. Geometry, well, I've got that total steric number of 4, so that's tetrahedral again. My shape, well, I have 0 lone pairs. So since I have 0 lone pairs, my shape is also tetrahedral. And my bond angle is going to be 109.5. And that is because I'm in this tetrahedral 109.5 again. Okay, there are no lone pairs, so I'm not going to say a little bit less than 109.5. Cool. All right, now here's NO3 minus, which, if you recall, displays resonance. And it's not important just to determine the shape for me to draw all resonance structures. I know that there are multiple resonance structures, but I just need to look at one to do TBL. Okay, now please be careful here. I'm looking at that central N, okay? And when I count my total, I'm going to say 1, 2, 3. Remember, the double bond just counts once because we're just really doing bonding site. So a double bond is only one bonding site. So my total is actually 3. Be careful, don't do a total of 4 there. My total is 3. All 3 are bonded, and I don't have any lone pairs, 3, 3, 0. My geometry, let's see, since my steric number is 3, my geometry is trigonal planar. I have no lone pairs, so that means, oops, I circled the one with lone pair. No lone pairs, that means it's also trigonal planar. And my bond angle here is going to be 120, coming straight from here. Now notice some of these bond angles kind of make sense, right? You have a 360-degree circle. If you divide that to 3, you get 120, right? When you have a linear thing that's half of the circle, it's 180. So some of them make some sense that way. Okay, so this is trigonal planar. Gonna sneeze, excuse me 1 second. Excuse me. Okay, and then here, let's say we have something like this, O2. A lot of times students say, Ms. Lula, which one is the central atom? Okay, the thing is, you don't have to worry about TBL. 2 dots only make a line, right? So all of these are going to be linear, okay? Because 2 dots can only make a line. Doesn't matter how you do that, they can only make a line. So when you only have 2 atoms in your molecule, it is automatically linear, no TBL required, okay? So just to remember that these are actually 3D molecules, this is our water molecule that we did, okay, that we said was bent in shape. This was our CCl4 molecule that we said was tetrahedral in shape. This was our NO3 minus, which we said was trigonal planar in shape. And I think these extra little dashed lines are to show the resonance. And then this is our O2, our H2, and our HBr, all linear molecules, okay? So that's how you determine the shape of a molecule. There's only one other thing I just thought of right now. I want to go ahead and add in. I can use some space right here. Sometimes you might get a molecule where you're really not sure what the central atom is. So let's say we had something like this. CH3OH. When you draw that, it looks like this. And so is the C the central atom or is the O the central atom? And the answer is they both are. So if a question was to ask you for the shape of this molecule, they would have to say, what is the shape around the C? Or they would have to say, what is the shape around the O? And when I do that, TBL, for the C, I get 440, which ends up giving me a tetrahedral shape. And when I do it for the O, it ends up giving me 422, which is bent in shape. So the truth is, CH3OH is going to be, I'm not very good at this 3D drawing, but I will try, is going to be a tetrahedral. Nope, that's not really what a tetrahedral looks like. That's what a tetrahedral looks like, so I need one more up here. Okay, it's going to be the CH3, and then here it's going to have like a bent OH off of it, so that we see the tetrahedral and the bent molecule coming off of it. So they would have to specify whether they're asking you about the shape around the C or around the O. Okay. Okay, so then the next thing we need to talk about is the polarity of the molecule. So we previously learned to identify if individual bonds are polar or nonpolar based on differences in electronegativity. We learned that the higher the difference in electronegativity, the more polar the bond, because the less evenly everything is being shared. Okay, but that is bond polarity. Okay, if a bond is polar, once we decide a bond is polar, we can draw a dipole moment for that bond. And remember, that's going to be that arrow that we use. But to determine if a molecule, like the overall molecule, is polar or nonpolar, we need to look at the overall dipole moment. Okay, so before we do that, just remember that polar molecules will have an uneven distribution of charge, which really means in this case electrons, and polar molecules will have an overall dipole moment. Nonpolar molecules will have an even distribution of charge, and it will not have an overall dipole moment. Okay, so here's an example. Looking at water. We already have the structure for water. There would be some lone pairs here, but they're not really relevant when we're talking about whether something is polar or nonpolar in this case, because we can see that we have these polar bonds, okay? So we have these polar bonds because O is more electronegative than H, which means there's a dipole moment going here and here. You can see that those are drawn in for us, okay? So those are the individual bond dipole moments. What we want to do is see, do those cancel out with each other, or is there an overall dipole moment? In this case, the right motion and the left motion of those arrows does cancel out, right? Right and left will cancel out to nothing. But both arrows are pointing upwards, which means there is an overall dipole moment for this molecule moving upwards. And therefore, water is a polar molecule. It's kind of like if you took physics, you might know when we like add up vectors. Basically, I'm trying to add up this arrow with this arrow. Any side motion is going to cancel out because they're going opposite of each other, but the up motion is going to add together. And so we have an overall dipole moving up, which makes water a polar molecule. Remember, water is bent. Bent molecules are always polar for this exact reason. Okay, here's our tetrahedral, which is carbon tetrachloride. And we did this example, we identified it as tetrahedral. You can see all of the dipole moments drawn here, okay? And you can see that we have this upward dipole moment right here, okay? And then we have these three downward dipole moments. Now, these three downward dipole moments are all moving in different directions. And the direction, kind of right, left, center, is all going to cancel out because they're all going to be evenly distributed around that 360 degrees. So really, when we add up these three bottom arrows, they really just add up to one downward shape, okay? And then we just have an up and a down, which is going to cancel out. Therefore, there is no overall dipole moment, and a tetrahedral is always a nonpolar molecule. So again, while there are individual bond dipoles, they actually all cancel each other out in direction, and therefore it is a nonpolar molecule. I actually find this one easier to see when I do it as a 2D drawing. Okay, chlorine is more electronegative, so the dipole moment goes up and down. Those are going to cancel each other this way and this way. Those are going to cancel each other, so there's no overall dipole moment of a tetrahedral. It's going to be a nonpolar molecule. Okay, now here's our nitrate ion. We again know that this displays resonance. And remember, this was trigonal planar. So it was planar, which means there's not other angles here, like 3D angles, because it's a planar molecule. And so I have an upward dipole moment here because O is more electronegative than N. I have this side one and this side one. Well, the right and left down ones, the right and left part of that cancel out because they're moving opposite. But the downward will add up to a downward one. But then the down dipole moment and the up dipole moment are going to cancel each other out. And this is going to be nonpolar. Now, one question that students might have is, wait a minute, is the dipole moment stronger for this double bond? And the answer is no, because remember, in resonance, this isn't a true double bond. This is actually flip-flopping, and these three bonds are actually equal in some average way. So we don't have to worry about the double bond or anything. Just know oxygen is more electronegative, so that's why I drew that dipole moment that way. Okay. Here are my O2, H2, and HBr. For these, there is only one bond. So if that bond is polar, the molecule is polar. Here, O and O have an electronegativity difference of 0. So this is a nonpolar bond and a nonpolar molecule. H and H, electronegativity difference of 0, nonpolar bond, nonpolar molecule. HBr, pretty decent electronegativity difference. So polar bond, polar molecule. No need to draw the dipole moment necessarily, but we could draw it towards the more electronegative atom. Cool. So that's pretty much all we need to do today. So the idea is molecules are 3D. It's important for us to be able to identify using our TBL method what geometry and shape we have. Most often on the AP exam, it does get a little bit confusing because a lot of people use the words geometry and shape as synonymous. So I always specify both. Like I'll say the electron geometry is tetrahedral, the shape is also tetrahedral. The electron geometry is tetrahedral, the shape is bent. I'll try to be as specific as possible, but you can always see what the question is asking you. Then you can identify whether it's polar or non-polar. Just to help you a little bit, because sometimes I know for me it's hard to understand the dipole moments canceling out. The ones I'm circling right now are all the non-polar ones, right? So our whole first line are non-polar, okay? These guys, they turn out to be linear. They end up being non-polar. And then this guy right here is square planar, and he ends up being non-polar as well. So I've just circled all the ones that are non-polar. All the ones not circled are the ones that are actually polar. So that might be helpful. Now, I figured that out by actually looking at these drawings and thinking about what would end up canceling out with each other, right? That's how I figured those out. But it might be helpful to see it like this. Okay, I think I had one more slide I had somewhere of some things to think about. Maybe here, some things that came up. Here they are. Okay, that come up, excuse me. The presence of a lone pair on a central atom, almost, I should say, always causes an uneven distribution of charge, making the molecule polar. So if you have a lone pair or multiple lone pairs on a central atom, you can pretty much assume that the molecule is going to be polar. The one exception to that is the square planar, and so that's why it's almost always. But if there's a central atom, I assume that it's going to be, if there's a lone pair on a central atom, I often assume it's going to be polar. Okay, the more lone pairs there are on a central atom, the smaller the bond angle becomes because there's more electron-electron repulsion. So that just means if I'm trigonal planar and I have a bond angle of 120, and then there's one lone pair, I'm going to remember to say that it's a little bit less than 120. Okay, you don't have to give an exact number. You just want to say it's less than 120. The more lone pairs there are, the more electron-electron repulsion there is, the smaller the bond angle becomes. Okay. A shape that is usually non-polar could become polar if the atoms attached to the central atom aren't all the same. So that's a little bit tricky. For example, a tetrahedral molecule, which could be CCl4, would be non-polar. But if I made it Cl3CF, okay, then because this F has a different electronegativity, the dipole moments will not actually cancel out. So I would have a dipole moment here, a dipole moment here, one here, and one here. These two would cancel out, but the dipole moment for CF is going to be different and stronger than the dipole moment for Cl. So this won't actually cancel out, And so then you would go ahead and say that this was a polar molecule. And you can always recognize that because remember, it's about even or uneven. Clearly, even if I don't worry about dipole moments, when I have 3 Cl's and then an F, this becomes an uneven molecule, and therefore this is going to be polar. So that might be something that's a little bit tricky that you might want to remember. Okay, cool. That rounds out what we need to cover for today. I hope you have a lovely day, and next class we will pick up with some hybridization, and then we'll move on to ionic and metallic bonding. Have a great day. Bye.